A solid solution is a solid-state solution of one or more solutes in a solvent. Such a mixture is considered a solution rather than a compound when the crystal structure of the solvent remains unchanged by addition of the solutes, and when the mixture remains in a single homogeneous phase. This often happens when the two elements involved are close together on the periodic table. Conversely, a chemical compound generally results when two metals involved are not near each other on the periodic table. The solid solution needs to be distinguished from a mechanical mixtures of powdered solids like two salts, sugar and salt, etc. The mechanical mixtures have total or partial miscibility gap in solid state. Examples of solid solutions include crystallized salts from the liquid mixture, metal alloys, moist solids. In the case of metal alloys, intermetallic compounds occur frequently. Application: in the phase diagram, at 3 different concentrations, the material will be solid until it's heated to its melting point, and then become liquid at that same temperature. The unalloyed extreme left, the unalloyed extreme right, the dip in the center. At other proportions, the material will enter a mushy opacity phase until it warms up to being completely melted. The mixture at the dip point of the diagram is called a eutectic alloy. Lead-tin mixtures formulated at that point are useful when soldering electronic components, particularly if done manually, since the solid phase is quickly entered as the solder cools. In contrast, when lead-tin mixtures were used to solder seams in automobile bodies, opacity state enabled a shape to be formed with a wooden paddle or tool, so a 70-30 lead-to-tin ratio was used. Exsolution: when a solid solution becomes unstable due to a lower temperature. For example, exsolution occurs and the two phases separate into distinct microscopic to megascopic lamellae. This is mainly caused by difference in cation size. Cations which have a large difference in radii are not likely to readily substitute. Take the alkali feldspar minerals for example, whose end members are albite Nal C308 and microcline Cal C308. At high temperatures Na+ and K+ readily substitute for each other, and so the minerals will form a solid solution. Yet at low temperatures albite can only substitute a small amount of K+, and the same applies for Na+ in the microcline. This leads to exsolution where they will separate into two separate phases. In the case of the alkali feldspar minerals, thin white albite layers will alternate between typically pink microcline